Hello students, we'll continue looking at the working of the cache, and today we are going to look at the third question, which is how to deal with a cache miss. We would say that a cache miss has happened if the data we are looking for using the address is not present in the cache. How do we find out? Again, we are based on the address mapping, the cache mapping, whether it is direct mapped or set associative or fully associative. We are going to pick the index and uh, check the tag bits that are present at that index, right? And if none of the tags match in case of fully associative cache or in case of set associative cache, um, none of the tags that were placed in that particular set match, then it's a miss. In case of direct map, the block is there is only one block, and we look at the tag beds, and if there is no match, it's called a miss. What to do upon a cache miss is there are two things. The very first thing is we are going to forward the request from this level of the memory hierarchy to the next level. For example, let's say we have three levels of cache: L1, L2, L3, and following that we have the main memory. Let's say the processor has requested for some data, and that we have looked up in the L1 and it was a miss. So what does L1 do? It forwards the same address to L2, and let's say if L2 also doesn't have it, then it forwards the request to L3. And if L3 doesn't have it, we forward it to the main memory. And if in case the main memory also does not have it, then it is handled by the operating system. And of course, we will forward the address to the storage, but that is done by the operating system. Within the caches, still the main memory, right? Everything is done by the hardware. So the cache controller will forward the address of a cache that resulted in a cache miss to the next level, and it uh, needs to find some empty space in that particular set also, so that when the lower level replies, let's say when if it was a miss in L1 and assuming that it was a hit in L2, L2 will reply with that block of data. So we need to place that data in L1, and so the L1 cache controller needs to find the appropriate space for it. Now, if there is some vacant space in that particular set, it means that that set is not full. Then the cache controller will pick that vacant spot and place the new block in it. This is a straightforward case. But if the set is full, what what to do? That's what this question is about. How do we pick the space or the spot for this new incoming block? And what it also means is one of the existing blocks in the set needs to be removed, or in technical term it's called evicted, and the block itself is called a victim block. So the cache controller needs to find a victim block and uh, send it to the next level of cache that we are going to see as part of next question also. And the important question now we are going to look at is how does the cache controller select a victim block? What the cache controller follows is called as a replacement policy. Replacement policy is pretty straightforward for the direct mapped caches, because there is only one block mapped to that particular set, and let's say the new request resulted in a mess. So whatever the lower level cache replies with, it needs to be placed in the same set, and what the existing block needs to be the victim block. So there is no big deal in it. It's pretty straightforward, and the decision making for the cache controller is simple. So in general, direct mapped caches are faster in terms of block replacement, because there is No confusion there. There's just one space, and whatever is there in that space need to be evicted. But for the set associative and fully associative caches, the set has multiple blocks mapped to it. Now the question is which one to choose. Accordingly, the replacement policy uh, can be a random policy, means we can pick one of those existing blocks at random, or uh, it can be the least recently used, in short LRU policy. And another policy can be first in first out, meaning that whichever block has entered the set first will be kicked out first, evicted first. So it's like our queue, right? So, or any other there are like tens of replacement policies that have been studied over the past 2 3 decades. For implementing the replacement policies, the cache controller needs extra information for each block, and this extra information will also be placed along with the tag, meaning in the tag array. So let's look at how the cache controller will be performing this or selecting the replacement candidate. And I'm going to pick the LRU policy because it is in line with the way the temporal locality works, right? If some particular block is being reused a lot of times every now and then it would be good to keep it in the cache, and LRU policy will help us to keep such blocks in the cache. So let's look at how the LRU policy would work. Now consider a four-way set associative cache. It means that each set has four blocks mapped to it, right? And consider the sequence of accesses B0, B1, B2, B3, B4, etc., all to the same set. So in this entire discussion, we are going to look at only one particular set of the cache, and whatever in general happens in this set can be extended to the other sets as well. So here, for simplicity in explaining, I have built a table. We have the column 1 as the requested block, which is one of these, right? And then whether that requested block access is a hit or a miss. And then the last four columns of this table are the recency list. So on the left side we have the head, and on the right side we have the tail. The head is also called most recently used, and the tail is the least recently used. So the first requested block was B0, and assume that the cache has started with all zeros. So the moment you switch on the processor, right, your laptop, anything, because it's volatile memory, cache and main memory, everything starts with a zero, right? There is no data stored in it. So the few first accesses will always be misses. It's called cold miss, or the this event is called cold start. So if somebody says that I've started, uh, I have the cache which starts cold, then it means that it is empty to begin with. So the very first access B0 is a miss, and it is placed in at the head of the recency list because it is the most recently used. Following that, let's say the next axis was for B1, and again B1 is a miss because it's not there in the cache. So now there will be a slight change in the recency list. The most recently used block would be B1, and the one which was accessed just before that is B0. Then the access was for B2. Again, it is a miss. B1 B0 in the recency list will move to the left, and the most recently used block would be B2 here. The next axis is for B3, and again it is a miss because it's not there, and B2, B1, B0 again are shifted left, right, and we make space for B3 at the MRU position. Now, if we look at the recency list at this point, it says that B0 was used at least 4 accesses before, and B1 was used at least 3 accesses before, B2 was used 1 access before, and the latest access was for B3. That's why it's called a recency list. Now, let's say the next request is for B4, and again it results in a miss. And at this point, uh, in the prior 3 misses or prior 4 misses, because the set had some empty position, we had placed the incoming block in that position, but here the set is full. Now the cache controller needs to pick one of these B3, B2, B1, B0 as its victim block. So because we are following LRU policy and B0 is in the LRU position, B0 is kicked out, or it's the victim block. So the other 3 blocks, B3, B2, B1, will be moved to the right, and B4 will be placed in the MRU position. Now, if we look at the recency list, it says that B4 was the most recently used and B1 is the least recently used, and B3, B2 fall in between them. Now, let's say the next axis is for B3. This results in a hit because B3 is already present in this particular set. So this will be a hit access, and now B3 will be placed in the MRU position and B4 slips 1 position down. B2, B1 will remain in the same positions. Now if the next axis is again for B4, then it is a hit, and B4 now comes to the MRU position and B3 goes to the MRU -1, let's call it that way, and B2, B1 continue in their respective positions. Now let's say the axis is for B2. This again is resulting in a hit because B2 is already there, and B2 now moves to the MRU position. B4, B3 will be shifted left, right, and then the LRU position continues to be held by B1. Now when B0 request comes, B0 is not there, it is a miss, so we need to pick a victim block. The cache controller will look at this particular set recency list, and it finds that B0 is the least recently used, so the B0 position will be given to, sorry, B1's position will be given to B0. So, and again B0 will be in the MRU, and B2, B4, B3 will shift to the right by 1 position. The last axis in our example sequence of axis is for B5, and it is resulting in a miss. At this point B3 is in LRU position, so B3 will be kicked out and B5 will be placed in its place, and the contents of this particular set are B5, B0, B2, B4, and B4 is the least recently used, B5 is the most recently used. So this way the cache controller can implement the LRU policy. It maintains a recency list. It needs to maintain a recency list. So to implement that in the actual hardware, each block is required to have 1 bit extra in its tag array to indicate whether it is a valid block or not. Like I said, when there is no block present in the cache, it needs to be represented as some state, right? So when the cache starts, all the blocks will be zeros, but their valid bit is also 0. That will say that it's not a valid data, because all zeros is also a data. So how does the cache controller know that it's a valid data or not? So we have a valid bit in it, and along with that we have to maintain the recency info, because it's a 4-way. We need 2 bits to maintain this recency info here, meaning each of the flow 4 blocks will be either having 0 0 0 1 1 0 or 1 1 as their recency info, and let's call that recency info as S bits here, status bits. And I would suggest you to redo the same experiment, meaning consider a four-way set associative cache and consider the same sequence of accesses, and try to implement a FIFO and see how the cache controller would implement it. And in the process you will also able to identify how many hits and misses are there. And you can also figure out if you need any additional info apart from this valid bit and recency info. So the recency info for FIFO would be handled differently, but still we need some additional bits. So figure out what needs to be done there. And how about the random policy? Do we need to have any extra information? Of course valid bit is needed, but do we need to have any recency info, anything like that? No, because at any given moment the cache controller will pick one of the 4 blocks at random. So we don't need any other status bits for random policy. Now let's dig further into the LRU policy and see how it is actually implemented in the hardware. Again, I'm considering the same 4-way set associative cache, and the sequence of accesses is same as prior, and all these accesses are to one particular set. So here we have a similar table. We have the requested block and whether it is a hit or miss. These are just for our understanding. These are not part of the hardware. What the hardware would have is in the tag array, because it's 4-way, we have 4 ways: way 0, way 1, way 2, way 3, right? And in each way we actually are storing the valid bit, the status bits, and the tag bits themselves. So this all these 4 ways are the tag arrays of this 4-way set associative cache. So earlier we were interpreting the last 4 columns as recency list, but that is just for our understanding. Now let's see how the hardware would handle it, or how we would implement LRU at the hardware. So like I mentioned, each way has valid bit, 2 bits of status, and the typical tag bits of each block. We start with the set having all the valid bits set to 0. Now the very first access was for B0. It is a miss because the cache controller will go and check that all the valid bits are 0 in here. So it is a miss, and it will place B0 in way 0, and it will also set the valid bit to be 1. Let's say that T0 is the uh, tag bit of B0. And we also need to set the status bits here. The highest value that we can have in 2-bit counter is 1 1, so it is 3. That is what is placed here by the cache controller. Now moving on to the next axis. Before that, just a side note that all the other ways still have valid bits as 0. The next axis is for B1. Again, it is a mess. How do we find out? This particular set is activated and all the tag bits are observed. One of them is 1, having valid bit as 1. So T0 is read out, and T0 and the tag bits of B1 are matched, and it will be a mismatch. So that's when we'll know that it's a miss. So accordingly, the cache controller will look for a space for to keep B1. In the first way, B0 is already there, so it will pick the way 1, whatever is there just beside that, whichever is empty, right? It sets way 1's valid bit to 1, and the tag bits of B1 are placed as T1 here. Now it also needs to maintain the recency info. Accordingly, the status bits in way 1 will be set to 3, and whatever status bit is there in way 0, it is decremented by 1, so it becomes 2. So just at this moment, if we want to understand how the set accesses were, it would say that wave, whatever data is there in wave 1, that is the most recently used, and whatever data is there in wave 0, that was used just before that, because their status are 3 and 2 respectively. Now let's move on to the next axis, which is B2. Again, the set will be read, and B2's tags are matched with T0 and T1, and that's when we will know that it's a miss. And it will the cache controller will look for some empty space now, because two valid bits are already 0. It means that there are two empty spaces in this set, so we don't need to uh, go for the replacement policy here. We have the empty space, so it will place in way 2. So way 2's valid bit is set to 1, and the T2 is the tag bits of B2, and way 3 will continue to okay, before that, the now the way 3 way 2's status bit will be set to 3. Then whatever is there in way 1 will be decremented by 1, so it becomes 2, and whatever is there in way 0, it becomes 1, and way 3 will continue to be in valid status of 0. Now let's say the next access is for B3. Again, it will result in a miss, and at this point it knows that the way 3 is empty, so the other three ways will continue to be having the same blocks with valid bit set to 1, and in way 3 we are going to place the new incoming block, which is B3. Its tag T3 is placed here. In addition to that, the recency information needs to be maintained. So way 3's status bit will be set to 3. Whatever is there in way 2 will become 2, and whatever is there in way 1, it becomes 1, and in way 0 now we have 0. Now at this point, if you look at the status bits, it says that B0 was the least recently used, and B3 was the most recently used. At this point, if a request comes for B4, now again we look up to all the tags and there is a mismatch, but here is the situation where we need to invoke the replacement policy. The cache controller, because it finds all the set is full, it needs to pick the victim candidate, and it will look for the block which has the status bits as set to 0 or the lowest of it. So here the lowest is 0 itself. So B3 will be the victim block. At this point, what it means is the cache controller will place B4 in way 0. So its tag is placed in T4, and its the valid status bit is continued as 1. And the other cache blocks will remain in the other ways. And now the recency info would look like uh, the way 0 will be having 3, and whatever is there in way 1, way 2, way 3 will be decremented by 1. So here it will be 0, it will be 1 here, and for way 3 it will be 2. Now moving on, the next axis was for B3. Now by looking at the tags, it will be a match, so it is a hit axis. At this point, we also still need to maintain the recency information. What it means is whatever value is there in the hit way, here it is way 3, it will be set to 3, and for all the other ways the value is decremented by 1. So in way 0 it will be 2, way 1 will continue to be 0, because you can imagine it to be a 2-bit saturating counter, so maximum is 3 and minimum is 0 only, and way 2 also becomes 0. Now if we look at this particular set at this moment, we would say that the data in way 3 was most recently used, and data in way 0 was used just one axis before that, and both way 1 and way 2 were used quite some time back, because both of them have status 0. Now let's say the next axis is for B4. Again, it is a hit, and similar to what happened just before this axis, and way 0 is the hit way here, so its status bit will be made 3, and all the other ways we would be decrementing. So way 3 will become way 3 status bits will become 2, and way 0 sorry, way 1 and way 2 will continue to be zeros. At this moment the next axis is for b2. Again b2 is already there because tag 2 will be a match, so it is a hit axis. Accordingly, the status bits of way 2 will be set to 3, and all the other ways status bits will be decremented by 1. So way 3 becomes way 3 status bit become 1, way 0 status bit becomes 2, and way 1 would continue to at the 0 status, right? 0 0. At this point now the axis is for b0. What the tags we have is T4, T1, T2, T3, T0 is not there, so it is a miss. Now at this point the cache controller will look for a block with status bit of 0, which is way 1 here. That means that this is our victim block, so that will be kicked out, and in its place B0 will be placed. So T0 is stored in way 1, and the other blocks will continue to be in the same ways. And now we need to carefully update the recency info. So way 1's status bit will be set to 3, and all the other ways it will be decremented by 1. So if we look at the set status at this point, and if you want to build the recency list like we have built in the previous slide, it would be B0 followed by B2, then B4, and lastly B3. That's how you can imagine that the recency list would look like, just by maintaining 2-bit status. And the last axis in our example axis is for B5. Again it is a miss. So now the cache controller would pick whatever data is there in way 3, whatever block data you can say, as the victim block, and in its place the B5 is stored. So its tag T5 is stored here, and its recency information, that is the status bits, will be set to 3, and for all the other blocks it will be decremented by 1. So at this point if we look at the if we try to imagine the recency list, it would be B5 followed by B0 followed by B2 and then B4. So B4 is in the least recently used position, and B5 is in the most recently used position. So that's how the cache controller needs to carefully maintain the recency info both upon a miss and upon a hit. And upon a miss, if it does not find any empty or vacant position in the set, then it needs to look at the recency bits and pick the guy with the lowest value. So that's how we would be implementing LRU at the hardware, right? And whatever we discussed is for one set, the same thing can be imagined for all the sets in the cache. So let's say your cache has um, 1024 sets, right? And if we assume that the cache is 4-way set associative cache, overall we have 4 times 1024 blocks, means 4k blocks are there, and for each of those blocks we need to maintain 1 bit of valid bit information and 2 bits of status information. Now what happens if your cache is not 4-way but 16-way set associative cache? At that point the cache controller needs to maintain not 2 bits but 4 bits of recency information for each block. Only then we will be able to distinguish which of those 16 blocks is in MRU and which is in LRU position. Okay, now the LRU replacement policy, as you have seen, that it will help us keep the most recently used blocks in the cache. So it was heavily used, and it was one of the most popular ones. And Typically, because the most recently used or most frequently used blocks will have non-zero status bit, they will not be the victim blocks. That is the rationale behind how it can exploit the temporal locality. Now, like I mentioned, if we move from 4-way to 16-way, the number of status bits will increase, right? And for each access to that particular set, one block will be set to the highest value, and all the blocks counter will decrement by one. It's too much effort for the cache controller, right? Every time for every access, we are changing 16 counters. Accordingly, the implementation of LRU for high associative caches, right, was discarded, or you can say because of the power and the implementation issues, it was slightly diluted. It means that we no longer look for a strict least recently used block, but rather we can go for something like pseudo LRU policy, or least frequently used policy, and some one other variant is not recently used policy. So here, instead of having 4 bits for a 16-way cache, 4 bits for block, probably we can work with even 2 bits, right? So uh, the implementation issues of LRU uh, were so high that people started looking for some new replacement policies also. Even though LRU exploits temporal locality better, they wanted to uh, make it more and more practical, meaning that the power area overhead should be less. So accordingly, many new and even complex replacement policies were developed. One of the most popular is RRIP, re-reference interval based uh, replacement policy, right? I'm going to share it in the additional information. Do go through it. It is based on the LRU policy itself, and the designers have come up with a very intuitive modification to the LRU to make it working better, and also implementation wise we will not need so many additional bits. Okay, and at this point we have what we have discussed is for direct mapped and set associative mapped caches. What happens for fully associative mapping? Imagine the previous example that I said, like we have 4 times 1024 blocks, right? Now if we want to implement LRU for a cache which has 4k blocks, imagine the number of status bits it needs, right? Among these 4k blocks, we need to find out which specifically is the least recently used, because all of them will belong to one set only, and that guy will be picked as the victim candidate. So because of these implementation issues, the fully associative caches are not so popular. Typically we have 16-way, or at most maybe 32-way in very specialized designs, but nothing beyond that. We don't have a fully associative cache as a normal cache. If it is try to imagine a 32 MB cache with 64-byte blocks, and for each block, if you want to specifically identify whether what is its status, whether it is MRU or LRU, there is too much of overhead. So the fully associative caches are not used at all, but they are used in some highly specialized uh, uh, places, like I mentioned in the branch target buffer. We don't need to require to maintain so many branches information. Typically few hundreds of branches would be sufficient. And in the next uh, main memory discussion, you'll also come across what's called as translation look aside buffers, TLBs in short. They also use their fully associative mapping. Again, their size is small, so whenever the size is small, fully associative caches can be implemented, but not for larger caches. Keep that in mind. And for the set associative caches, the replacement policy mostly used is LRU. or a variant of it, which is RRIP in the current day. With that, I also want to give you some practice examples, right? So consider a four-way set associative cache here, and for one round, try to work with these access patterns in 1, 2, 3, 4, and look at how LRU policy would be implemented and how FIFO would be implemented, and at the same time you'll also know how many hits and misses are there. So keep check which of these policies gives us more hits. And so if you look at the each of those axis patterns here, the first axis pattern is b0, b1, b2, b3, so on to b8, and then the blocks are again b7, b6, b5, so on and so forth, right? We have uh, it's like accessing the array elements first to last and then from last to first. If you look at the second axis pattern, it is b0 to b7. The same axis is repeating multiple times. If you look at the third axis pattern, here there is no repetition. It's like the sequence. All the elements of the array are let's imagine a huge array, and we are going from element 1 to element n, and we are using them only once, right? And this is the third uh, example is more generally called as stream accesses, because there is no reuse there. We just see an increase or decrease in the addresses, right? And there can be a combination of all the three here. So the second one is repetition, and the first one has some temporal locality. The third one does not have any temporal locality. So if you are able to figure out for which the LRU policy is the best, for which type of accesses and all, when you read the RRIP paper, you will understand what extra benefit we would get with RRIP. With the re-reference interval policy, we would be able to still capture uh, the accesses which belong to 1 and 2 here. With that, I will pause this lecture. Thank you.